Okay, so I keep forgetting to record the meets, but here we go. So I'm just gonna restate everything I said in video form so you guys who weren't here can watch this. So basically the two videos that we looked at first reviewed everything we know about Newtonian physics. So how objects act on Earth, how they act in space, okay, what we know about free fall, what we know about objects that are orbiting, and how we measure those things. The second video basically asked us to pretend that all of that, everything we know about Newtonian physics, what we know about gravity, is an illusion. And that it's actually the opposite. Okay, so we're not at all stationary. We're not a stationary observer. We're not looking at an inertial reference frame. We are actually accelerating. And all the objects in which we are observing the motion of and measuring the motion of, those objects are moving at a straight line, or in a straight line, at a constant rate along space-time. They appear to us to be accelerating because we are accelerating. Okay, so let's take a few steps back. So basically here, what we have in yellow is what we know about Newtonian physics, which assumes that we are an inertial reference frame, meaning that we are stationary observers, and we are measuring the motion of objects around us. Newton described a gravitational force as an attraction between two objects with mass, right? If an object's close to Earth's surface, it will accelerate downward at a constant rate of 9.8 meters per second squared until it reaches a terminal velocity, if there's air resistance. If there's no air resistance, it's going to continue to accelerate at 9.8 meters per second squared until it hits Earth's surface. Right? And we know we have equations, sets of equations that accurately model this, right? We've done it in lab. Our marbles have hit the targets. We've used what we know about constant acceleration to predict how objects move, right? We know that those equations are accurate if we assume that we're a stationary reference point. Okay, Newton also explained that orbiting objects are in free fall. Okay, so objects are continuously falling, and their path of motion matches the curvature of Earth's surface, so that when the object falls, the surface curves below it. So no matter how long it's falling for, it never gets any closer to the surface of Earth. We call that object, although it's still in free fall, it's in orbit. It's orbiting Earth's surface. When objects are close to Earth's surface, we can use F equals ma to model the acceleration rate based on the net force. Okay, so objects are in free fall because of a constant gravitational force, which is equal to the object's mass times our value for g, 9.8. When objects are not close to Earth's surface, when they are in space or they're orbiting a distance above our atmosphere, Newton had to come up with a new mathematical relationship because those objects do not accelerate at 9.8 meters per second. Rather, he explained that the force of attraction varies, right? It's dependent upon the magnitudes of the masses, and it's inversely proportional to the square of the distance between the centers of those objects, right? So you have big G, m1 times m2 over r squared. So if the object is not close to Earth's surface, we use his equation for universal gravitation to find the force of gravity. Right? If an object's on Earth, we use the second law to model the force on an object. Newton's idea of universal gravitation matched and coincided with Kepler's laws. So basically, Newton invented calculus. He used calculus to prove that his laws were accurate and valid. Then Kepler came up with laws to describe why objects move in elliptical paths around the sun. Newton then made sure, to kind of consolidate all three of those ideas so that they work together to explain how objects move. Okay, so Newton invented calculus. Calculus proved the validity of his laws. His laws were then further enforced by Kepler's laws. Okay, so that's Newtonian physics. We can explain, assuming that our frame of reference is stationary, we can explain how objects move on Earth and why objects move on Earth. We can also explain how objects will move in space and why objects move that way in space. Great. Okay. Then, in 1905, Albert Einstein basically blew this all up, and it took several years to kind of marry these two ideas. Okay, so basically, Einstein asked a very important question. And because that question could not either be validated or disproven, it had to be researched, right? So this question could have basically disproved all we knew from Newton and Kepler. So that question that he asked is basically, how can we tell the difference between gravity and acceleration? How can you tell that when an apple falls from a tree, that the apple accelerates downward towards the ground versus that the apple is stationary and the ground is accelerating to meet it? From our perspective, those two situations would look exactly the same. They would appear exactly the same. So can we really state with definite certainty that the ground is not accelerating towards the apple? Well, no, we can't. But that would kind of take away from the validity of the laws that we already had used and practiced and had proven worked. So what Einstein did is he came up with something that he called the equivalence principle, which explained that there really is no difference. There's no way to determine the difference between free fall and lack of gravity. And that free fall Sorry, I'm getting a lot of emails and I just lost my train of thought. Okay. So due to the curvature of space-time, objects that appear to us to be in free fall, are actually not accelerating. We are accelerating. And those objects are moving in a straight line at a constant velocity. Okay, so he related free fall and a lack of gravitational force to each other. Okay, and from the reference frame that we're accelerating, that would actually be accurate. So Einstein's theory of relativity basically explains that Earth is a curved space-time. Okay, you are accelerating, we are accelerating, and the satellites that are orbiting Earth are actually moving at a constant speed in a straight line. If you're thinking to yourself, how can an object that's moving in a circle, based on what I'm seeing, actually be moving in a straight line? Well, that's a great question. So technically, space-time is 4 dimensions. We can only observe and experience 3 of those 4 dimensions. So what we're observing is not reality. Based on geometry in our next set of videos, it will show you exactly how we can be perceiving a parabolic path when in reality it's moving in a straight line. Okay, So general synopsis here, right? A reference frame is basically how you measure motion. Okay, so it's a criteria in which you make measurements based off of. So if you say that you're an inertial reference frame, Newtonian physics is accurate. If you say you're an accelerating reference frame, you are accelerating, then relativity is accurate. Okay, so it depends on your frame of reference in which you, as a physicist, right, decide. You determine the direction of acceleration of a pulley, an Atwood machine, based on the motion of M1 and M2. So based on the reference frame in which you choose, either Newtonian physics or relativity would be more accurate. What relativity is, it's really just the study of space-time and gravitational forces in relationship to each other. Okay, so Einstein, which this was proven in 2016, Einstein basically explained that space and time are intertwined along the plane of the universe and that gravitational waves move about that plane. And we detected gravitational waves in 2016 for the first time. So that is evidence to suggest that that theory is correct. The idea of space-time is so complex that I don't even understand it in full. Okay, I understand the most basic components of it and very simple models, basically how length is contracted and time is stretched. I know equations to model it. I can explain how those equations model it. But in a deep conceptual level, understanding space-time is very, very difficult. Okay, there's basically Einstein wrote a 3,000-page book about space-time. Haven't read the book. Not sure I'll be able to handle it, but if you're really interested in knowing everything about space-time, I suggest that you take a look at that. Okay, so basically our final piece of information here. Newton says that gravity is a force that attracts all objects and masses towards each other. Okay, and that force causes acceleration because we are stationary. Newton also says that free fall only occurs because objects have a force of gravity acting on them. Right? Forces of gravity cause constant acceleration. That's what Newton said. Einstein says acceleration, okay, occurs due to the curvature of space-time. So objects roll down the curvature towards each other. As they roll down space-time towards each other, they exhibit gravitational attraction towards one another. So it's a movement along space-time. Free fall, when objects are in free fall, it's actually the lack of gravity acting on them. So they are free to move if there is no gravitational force acting on them. We are accelerating. Those objects, satellites, are moving at constant velocity around Earth's surface, around the curvature of space-time, in a straight line. We are accelerating. Okay, so two questions that we probably have are, how does a curve in space-time cause an arc to look like a straight line to us, and vice versa? That will be answered in our next video. And the question is, how is force, aka how is gravity, actually just acceleration in the lack of presence of a gravitational field? We're going to take a look at inside the mind of Einstein and take a look at how he related that gravity is actually acceleration, okay, and not the presence of a gravitational field. Okay, and the next question that we'll take a look at is, can a straight line be a circle, and can a circle be a straight line? All right, so if you didn't already, please make sure that you watch those 2 videos. They're very interesting. They are a little confusing, but this video should help. And fill out that KWL chart just to kind of track your progress, to see what questions you have, what you're understanding, what you're not understanding. All right, have a great rest of your day, and I will talk to you guys tomorrow.